and vector functions unit. These are some questions that a student emailed to me. As you know that in the content, some of the questions don't show the work. They only show the solution. So I'm going to go over page 5, or on page 5, number 5 and number 6. If you would like to have a copy of the PDF file that you see on your screen, you can go to the chat box, and it's in the Google Drive box. So it's not the first link, but it's the second link that I posted, where it says drive.google.com. Remember, to access those files in the Google Drive, you do need to be logged into your Georgia Virtual School Gmail account. That is the only way that you can gain access. So if you need to open your email first, then click that link, please do so. And we're going to go ahead and get started with number 5. It says, find the area of the region that lies inside the curve r equals 2 plus sine theta, and outside the curve r equals sine theta. So what I did is I used Graphmatica to graph each of the polar curves. You can do this by hand as well, but since this particular recording is over area, I'm not going to go back and go over how to graph the polar curves. However, if you do need that, let me know and I can make a recording on that as well. So as you can see, I have r equals sine of t is the white graph, which is this one, and r equals 2 plus sine of t is the pink graph, which it's also the area that we're trying to find is shaded in pink, but also the graph is in pink, so r equals 2 sine of t. And it says to find the area of the region that lies inside the curve r equals 2 sine theta and outside. So or outside the curve of r sine theta. So what we're looking for is the area between those two. And I did, in fact, zoom in here. You can't see it here, but when I did graph this in Graphmatica, I wanted to, really take a look at what's going on in this area right here to see if there, was anything that went above the graph, below the graph, the intersections and all of that. And they do, in fact, this smaller circle is completely enclosed by the larger polar curve. So that wasn't going to cause me any problems. And they actually intersect right here, a little bit above where my arrow is, that right there. So therefore, the area of the shaded region is going to be the area of the large, somewhat circle. It's not really a circle, but the area of the large curve. Subtract the area of the small curve. The hardest part about this is determining the limits of integration using the graphs or you can use tables. So that's really what I'm going to try to focus on today, is reviewing how to find those limits of integration. If you were to make a table and graph, let's look at the first one, which is r equals 2 sine of t from 0 to 2 pi. If you were to actually make a table for that, you would see that starting here at the origin, it would actually give you, let me see if I can not pan this. There we go. It would give you from 0 to 2 pi each of these. Yeah, I won't do that, but it'll give you each of these points all the way around without repeating any r values. So let me see if I can figure out a different way to explain that, just in case that wasn't clear. If you make a table, see if I can get a little table here. If you make a table and you go from, let's say this is theta, but I'm going to say t. Oh, wait, hold on. That's not what I want to do. I want to put t over here. Sorry. If this is r, And if we plug in 2 plus sine of t in, and we start with 0, and then you might go to like pi over 4, then you might go to pi over 2, then you might go to pi, and so forth. And, you know, if you couldn't really see a good pattern there, you might want to even split it up further than that into smaller increments. But what you will find is it will take you all the way to 2 pi before you start repeating. And once you get to 2 pi, you'll find that you get the same answer here as what you got for 0, whatever that may be. So that one full cycle, or one full period as we might call it, is 0 to 2 pi. So that is in particular for this one, r equals 2 sine of t. So for the limits of integration, for the area of that entire polar curve that encloses that entire polar curve, I am going to use the formula for the area from 0 to 2 pi. Pan that up, sorry about that. So again, we're going to use 0 to 2 pi. And once you solve for that, and again, we're not going over integration today because I know you, looks like I have, never mind, that's right. Did I get the answer? Yes, you just can't see it because I need to zoom in on it because it looks like a subtraction sign, didn't it? And it is not. The area, once you solve for the integral, is 9 pi over 2. So that is 9 pi over 2 is the area of the entire portion within the larger circle. So what we want to do now is subtract the area of the smaller polar curve, which this one is in fact a perfect circle. But we need to know the limits of integration for that. So once again, in explaining that, if I do this, and I will start over, this is how you would figure out how to calculate the limits of integration. Is you would, again, make your table. And this time you're going to be plugging in 3 sine of t. And what you'll find is that you get a full polar curve with only, it would actually, instead of starting over at 2 pi this time, this one is going to start over at pi. So the answer you get when you plug in 3 sine of t that is one full curve. So if you went all the way to 2 pi, what would happen is you would start here, you would get one circle for 0 to pi, then you get another circle from pi to 2 pi, and then you've actually got 2 circles. So if you calculate the integral from 0 to 2 pi, you're going to have double the area that you need. So hopefully that makes sense. But that is how you're going to find the limit of integration. Is, take a look at your table. If you also, there's probably some applets online available. Well, actually, I know there are, but I couldn't find them this morning. I'll have to take a look and see if I can, and then maybe put it into the Google Docs as well. But you will, if you actually see it sketched out from 0 to 2 pi, you can see how long it takes to get one curve. Sometimes it might take 2 pi, it might take 4 pi, just depending on whatever the function is. You'll have to evaluate that. And that's the hardest part about finding the area within a polar curve, is finding those limits of integration. So now that we know from 0 to pi is one full circle, or 1 full period, we can now take a look at the calculations for that. Here at the top of the page, I'll zoom in here. So in finding that, we see that from 0 to pi, I'm using what I did, which just in case you missed it on the first one, I used the formula for the area of a polar curve, and that formula is the integral of 1/2 r squared d theta, or you'll see actually that I'm using here dt, t standing for theta, because in the integral calculator as well as in my Graphmatica graphing utility, I cannot enter the symbol theta, so I had to use t, and that is understood within those applications. So I found that the area of the small circle is 9 pi over 4. So to find the area between them, I'm going to take 9 pi over 2, which remember was the area of the large curve, subtract the area of the small curve, and then I get the total area in between them. So the final answer is 9 pi over 4. Let me know if you have any questions at all about that. Now moving on to number 6. Okay, let's read this one now, just in case you don't remember doing it. Estimate to the nearest hundredth the area that lies inside both r equals 3 plus sine 5 theta and r equals 6 sine theta. Okay, this one actually takes an entirely new approach. I graphed these in Graphmatica again and shaded the region in which we want to find the area of. It needs to be the overlapping area between those two polar curves. Well, here's the problem. I thought, you might think to yourself, okay, well, I need to find this area. So why don't I just find this point and this point, and then just integrate it to find the area of this particular portion. Well, that doesn't really work because we still have a little bit down here of the circle. And let me show you the picture really quick. Or, well, I'll show you in the next slide. The next slide here. But what we do need to find the points of intersection. And that's because we're going to end up having to divide this up in more than one way. I'm going to find the points of intersection one of two ways. You can either set them equal and solve for t, or in this case, since we only need it rounded to the nearest hundredth, we can use the graphing utility. So what I did within Graphmatica is I was able to hover my mouse at the point of intersection of both of these points, and I found, just because Graphmatica gave it to me, 0.18 pi and 0.82 pi. And the r values of each of those are the same, of course, because we can see that these polar curves are symmetric about the axis, the t-axis or the theta. So we have 0.18 pi and 3.26. So I do know what these two values are for r. So I went ahead, and because we don't even, we were just asked to find the nearest hundredth, I just went ahead and did 0.18 pi equals 0.57 and 0.82 pi equals 9.87. If you want to, if you did solve these by setting them equal to each other, you could find it without rounding to the nearest hundredth if you had to. So it actually took me a little bit to figure out, now how am I going to do this? I can't subtract one, I can't find the area of one and subtract the area of the other. That's not going to work. If you have any question about that, just, go through your mind and try to work all those out. And none of those scenarios are going to work out. I mean, this one really takes some thought. So after looking at this for a while, I realized that I could do this. I could split, and I'm really just looking at this first quadrant here because what's going on over here is the same. So if I just find the area of these two sections, then I would multiply it by 2 at the end. But this is easy. This blue section here, this sector, I can do that because that's just a portion of the area of the circle. So this is the area of the circle from 0 to, what point was that again? Do you guys remember? It was 0.57. Let's go back up to the previous page and make sure. Got to scroll it down. Yes. So this point had a value of 0.57 for r. So I can use the integral of the function, 1/2 of the function squared, from 0 to 0.57. And the circle, again, was r equals sine of t. So I can do the area of r equals sine of t from 0 to 0.57. And that will give me the shaded region in blue. To find the shaded region in green, I can find the area of r equals sine of 5t from 0.57 to up here at pi over 2. So, and then once I get this green section and this blue section, I'll just multiply it by 2. So let's see if I have that worked out on this page, or I have part of it worked out here. So even though I put into my integral calculator, and if you want to know which one that I used this one right here. I'll type it into the chat box. Okay, it's the last one there, that integral calculator. So I just put into the integral calculator the boundaries, which you'll find on that web page. They're on the right-hand side. If you do have any questions about using that, let me know. And then I had 1/2, and then what was it? 1/2 times 6 sine t. Well, what it did was it took 6 squared is 36 and divided it by 2 because of the 1/2, and that gives us 18. So that's why it gave me this note here: your input has been rewritten or simplified. So that's fine. I don't care. I know I put it in right, and I did check and make sure that it did simplify to the integral that I want to take. And then again, my boundaries were 0 to 0.57. Look at that. That's kind of crazy. And I did find an approximation, which is 1.04. And remember, we do only have to approximate this one. Yay. So we can use the integral calculator, and we don't have to find out anything exact in terms of pi or square roots or anything. So I got that one. Now I also need to do the next one, which, okay, is up here. Take a look. The area of r equals sine of 5t from 0.57 to pi over 2. So panning down, there it is, right, where is it? Here. Okay, sorry, I really should have a line in between these two because when I copied and pasted, these are two separate problems. This was our approximation of one, and here's our final answer for the approximation of the other. So again, it did simplify what I put in, which was 1/2 times f of x squared. So it simplified that, worked it out, found the integral, and then used the boundaries to calculate the approximation, which was 4.1653. So remember that we wanted to add those together, and that only found the area in the first quadrant. And then we decided to multiply that by 2, and that would give us the area of the first and the second. And there was no area below our polar our pole. There's no area below the pole, so we don't even have to worry about that. So this area was, the blue shaded area was a little over 1. The area was a little over 1. It was 1.04. And then this green shaded area, not including over here, but just over here, was a little over 4. So again, we needed to add those two together and then multiply by 2. And you get an approximation of 10.4128 to be entirely correct, especially if we are on the AP exam. We better do it right and round to the nearest 100th. And so we can put it as approximately 10.41, because you never know, those AP graders might take points off because they might think, oh, well, they don't even know how to round to the nearest 100th, or they didn't read the question carefully. So I really hope that that helps you. I want to direct your attention to the chat box and go over the links that I provided. The first link there is a YouTube. It's from Patrick JMT, which, as you all already know, is one of my favorites. And that is his YouTube channel with a search for polar area. You will find tons of examples there. And you can go, I mean, there's probably like 4 or 5 examples for finding the area of polar curves or finding the area between 2 polar curves. Then I already pointed out the second one, which was our Google Drive. I have a lot of files there in our Google Drive. And then lastly, if you had any problems opening on page 5, there was an applet for polar curves. Java has a new update that is blocking a lot of applications. So if you need some help on how to, I guess, bypass that so that you can use the applets provided within the course, then click on that link and you will find directions on how to manually bypass that. So I hope this recording helped you today. If you have any questions, let me know. If you have any other topics